In this video, we'll look at the notes for section 1.8 on Laplace's equation. The Laplacian has an R2 version and an R3 version. In R2, the Laplacian of u is equal to the second partial of u with respect to x plus the second partial of u with respect to y. In R3, we have the same thing, but then we just add in a second partial of u with respect to z. These give us the Laplacians of u in R2 and R3. So what does this represent physically? Let's suppose that h is a small real number. Then we can use Taylor's theorem to write down u evaluated at a small increment from x. So u evaluated at x plus h, comma y. So leaving y fixed, but incrementing x by a small amount h. Taylor's theorem tells us that we can write that out as this expression. So what is that? That's u at x comma y plus the partial of u with respect to x times h. Remember, y is being left constant here. It's x that we're incrementing, which is why we're just looking at partial derivatives with respect to x. And then we have the second derivative term with an h squared, and then we have the third derivative term with an h cubed, and so on and so forth. The next one would be a fourth derivative term with an h to the fourth, divided by 4 factorial, and so on and so forth. We can do the same thing with x minus h, and then we get essentially the same thing, except for every even term gives us a minus h instead of a positive h. Well, I say an even term, I mean the odd derivative terms, but even in the sense that this is the second one we write down and this is the fourth one we write down. But all of the ones that have an odd number derivative, those all give us a negative h. So we have a negative h there. Of course, we have a negative h in the other terms as well, but negative h raised to an even power is going to give you the same thing as positive h raised to that even power. At any rate, what we're going to do is we're going to add these two together. So we're going to just add those two terms. So we're going to have u at x plus h comma y plus u at x minus h comma y. Now what happens if we add these things together? Well, the first thing to notice is that all of the terms with h to an odd power are going to cancel out, because here I have an h and here I have a negative h, so those will cancel. Here I have an h cubed and here it's the opposite of h cubed, which again is negative, so those will cancel. All of the odd powers will give you a positive h and a negative h. I shouldn't say positive h and negative h, I should say h and the opposite of h. Those terms will cancel, leaving us only the terms with an even order derivative or an even power on h. So those all double. So here we have a u at xy plus u at xy, so that gives us twice u at xy. Here we have u, the second derivative of u with respect to x times h squared divided by 2 factorial. And we have the same thing in the denominator, we have the same thing in the second line, because negative h squared is the same as positive h squared. So those double up as well. So then we have 2 of those. And the next one we'll have, since the h to the 3 terms cancel, the next one will be an h to the 4th term. So that will be the 4th derivative of u, and we have 2 of those. So what do we do now? Well, what we're actually going to do is we're going to make a statement about the second derivative. So what the plan is to solve for the second derivative of u. So let's look at this term. We want to solve for the second derivative of u. That's our objective here. So what do we do? Well, the first thing we do is we notice that on the left side we have this term, u at x plus h comma y plus u at x minus h comma y, and that goes here, and there's also another term there. Next we have this 2u at xy. So we're going to subtract that to the other side, and that's going to be that term. Maybe we should put that as a color as well. So let's make that purple. So there's that one. And then we have a bunch of other terms. Everything else we just sort of group together. So all of these other terms we just group together. There are just a bunch of terms of order h to the 4th. So all of these terms are going to have an h to the 4th. The next one's going to have an h to the 6th. The next one is h to the 8th. In particular, you have a bunch of h's in them. The idea is that h is small, so eventually we're going to look at a limit, so these sorts of things are going to just disappear. All right, so what do we do now? What is the next thing that we do? Well, we're going to divide by h squared. So we're going to divide by this h squared term. So let's once again find another color here. Let's just pick this one. So we're going to divide by this h squared, so that's over there. Now notice that now here we have terms of order not h4, but h to the 4th divided by h squared is h squared. So then the next one would be h to the 6th divided by h to the 2, which is h to the 4, and then so on and so forth. But they're all going to have terms of h squared or h to something bigger. Okay, so other than that, we've left everything the same. So all of this is the same as all of that. So what's next? Well, we're imagining that h is a really small increment. So if h is really small, then all of these terms of order h squared or some power h to the bigger to a bigger number, all of those terms are going to be approximately 0. So we're just going to neglect those terms and just change this from an equality to an approximation. So what we have is that the second partial with respect to x is approximately equal to this difference here, divided by h squared. So it's u at x plus h comma y plus u at x minus h comma y minus 2 times u xy, which we've written here in the middle. Now it's also true that we can do the same thing for the second partial with respect to y, and we've done that here. Now we're going to end up with the same approximate equality. The only difference is that we're incrementing y here instead of x. So that's the difference. So if we add these two terms together, here we have the second partial with respect to x, and here we have the second partial with respect to y. If we add those together, that's going to give us the two-dimensional Laplacian of u. So that's approximately equal to the sum of these two fractions. Notice they have the same denominator, so we can just add them together. So here we have u incremented with x plus h, and over here it's x minus h. So maybe again we should just label these. So here we have x plus h, that goes to this one right here. And here we have x minus h, that goes to this one right there. And here we have the u x comma y, and here's another u x comma y. They both have a minus 2 in front, so if we add them together we get a minus 4 times u x y, and that leaves us with the y increment terms. So we have, here's y plus h, which goes there, and we need some other color, so y minus h, that goes there. So all of the terms are accounted for. Now, Laplace's equation is that the Laplacian of u is equal to 0. So what does that mean here if the Laplacian is equal to 0? Well, if the Laplacian is equal to 0, then all of this numerator is equal to 0. So if the Laplacian of u is equal to 0, then we have a 0 here. So h is not going to be 0. H is some small increment. So this numerator must be 0, or approximately 0. So what does that tell you? Well, let's solve for this term right here, the uxy term. So we want to solve for the uxy term, so that's there. So there's a 4 in the numerator, so we're going to end up dividing by that. So that 4 in the denominator is, so this 4 in the denominator is that 4 right there. So what are we going to do? We're going to get, basically just going to add this to the other side. And that's how it ends up over here with a positive 4. So we have a 4u at xy. You add this to the other side, which this thing is 0. And so then you end up with a 4 times u. And then you divide by that 4, and that's where that 4 comes from here. So everything else on on the right side is really unchanged. So we have the x plus h term there, and we have the y plus h term there. We have the x minus h term there, and finally we have the y minus h term here. So what does this mean? What does this mean geometrically, or what does this mean physically? This means that this quantity, u at x comma y, is approximately the average of the temperatures at the points that are close to it. So look at what these are actually saying to us. We're computing u at x comma y, and so we're looking at u evaluated at the point x plus h comma y, which is this one, x comma y plus h, which is that one, where then we're adding in u at x minus h comma y, which is that point, and u at x comma y minus h, which is that point. Now if you look at these on a graph, x comma y is some point, and in order to get to these four other points, you just move to the left or the right by h, or up or down by h. So if we really wanted to, we could just color code all of these points, which probably we don't need to do, but why not? So this is the x plus h term, and then we want orange for the y plus h term, that's this one, and then green for the x minus h term, which goes here, and then finally we have the y minus h term, which is right here. So we're computing the temperature at the point xy, and we see that it's approximately equal to the average of the temperatures of these points around it, these 4 points. Now these points are arbitrarily close because h is arbitrarily small. Now in fact this can be extended to a circle. So if you let c sub h be a circle with center at some point, let's call it x0, y0 for the time being, and let's say that it's a circle with radius h, so it's this circle right here. We've changed from looking at x comma y to a point x0 comma y0 because we're going to integrate, and we need our xy to integrate. So we have some point, that's our middle point, so to speak, and we're looking at a circle of arbitrary radius. So the radius of the circle is h, where h is some small number, and we're going to look at a circle oriented counterclockwise. So it can be shown, and it should be believable based on what we just saw here, that u at x0, y0 is the average value. So the average value along this circle, if you want to compute the average value along the circle, that is a line integral. So I said c, but it should really be ch. So you integrate u over ch and divide by 2 pi h, which is the circumference of the circle. This is a line integral. So it's a line integral along the curve ch taken counterclockwise. And this gives us the average value. So it can be shown that this average value is actually equal to the temperature at the center. So it's u at x0, y0. So in particular, as it says here, in particular, if u at x0, y0 is the average of the values of the points around x0, y0, having distance h away, where h is arbitrary, then in particular, u at x0, y0 cannot be a local maximum or a local minimum, because it's the average. So that means there must be a larger value or a smaller value further away from it, a larger value and a smaller value. So this value, u at x0, y0, so u evaluated at the center of this circle, can't be a local maximum or a local minimum, because at any arbitrary distance away from it, there's something larger and something smaller, assuming u is not constant, of course. Since this point was chosen arbitrarily inside the interior of omega, just inside it, not on the boundary, it follows that the maximum and minimum values must be on the actual boundary and nowhere inside, because if you find any point in the interior of omega, you can always find a circle around that point. So this tells us that the maximum and minimum values are always attained on the boundary, and that is a powerful piece of information, which is called the maximum principle. Let's talk about Laplace's equation in polar coordinates. Really, this is just an exercise in changing our coordinates from Cartesian coordinates or rectangular coordinates into polar coordinates. So we want to rewrite the Laplacian of u in terms of r and theta. And this is just an exercise in using the chain rule and the product rule. So how's this going to work? We know that the Laplacian is the second derivative of u with respect to x plus the second derivative of y with respect to x. This is polar coordinates, so we're just looking at r2. So we know that x is equal to r cosine theta and y is equal to r sine theta. So we want to compute the second derivative of u with respect to r and the second derivative of u with respect to theta and see what the relationship is between those two. All right, so du by dr, remember, x here is a function of both r and theta. Same with y, both r and theta. So du dr is going to be du dx times dx dr plus du dy times dy dr, because u is a function of x and y, and x is a function of r and theta, and y is a function of r and theta. So we're just using the chain rule here. But we can compute these. Well, we don't know anything about du dx or du dy, but we certainly know that the derivative of x with respect to r is cosine theta. And we know that, let's color code these things. So we know that the derivative of x with respect to r is cosine theta. And we know that the derivative of y with respect to r is sine of theta. Okay, so that gives it, so if we now want to compute the derivative of u with respect to r twice, so d squared u, dr squared, so if we want to compute the second derivative, that means we compute the derivative of the first derivative. So this is the first derivative right here, u sub r, which I'll write it that way because I'm running out of room there. Okay, so we want to compute the derivative of ur. And that's what we do in the next line here, in this line. So it's going to be the derivative of this quantity. So importantly here, cosine of theta doesn't depend on r, and nor does sine theta. So if you want to compute the derivative of this quantity in the box, the cosine theta and sine theta terms, those are constant with respect to r. So this sine theta is that sine theta, and this cosine theta is that cosine theta. So what we want to compute is we want to compute the derivative with respect to r of du dx. So that's going to give us the derivative of u with respect to x, which is that term, times the derivative of x with respect to r. Now, the derivative of x with respect to r, again, is cosine, so we're going to end up with a cosine squared term here. Now the next thing is we want to compute the derivative of, so the derivative with respect to r of du dy. That's this one right here. So that's going to be the derivative of u dy with respect to y, so that's going to give us that, times dy dr. But the derivative of y with respect to r is again sine of theta. So you're going to end up with another sine of theta here. So this term is that term right there. Okay, so once you have this is the second derivative of u with respect to r. The next thing to do is find the second derivative of u with respect to theta, which we've done here. So again, we use the chain rule. Du dx and du dy, we don't exactly know what those are at the moment, but we do know that dx d theta is minus r sine theta, and dy d theta is r cosine theta. Once again, we want to compute the second derivative, but now we have extra thetas around. So computing the derivative with respect to theta is going to require a couple uses of the chain rule. So, a couple uses of the product rule, and also the chain rule. So we want to differentiate this expression that we're putting in a box here. We want to differentiate that with respect to theta. So that's the derivative of the first term, so du dx with respect to theta times the second term right there, plus the first term, which is du dx, times the derivative of the second term, which is that. So we've just used the product rule on this first term here. So it's the derivative of the first term times the second term plus the first term times the derivative of the second term, which is what we've written down here. We haven't computed it yet. So that's just the derivative of this first product. So that goes to all of this. And then we do the same thing for this term right here. That's all of this. That's all of that. So if you simplify that, you get this expression. So the second derivative of u with respect to theta, so this is the bottom half, and then we have the top half here. Now notice that when you're differentiating this term right here, so the d theta du dx, what's that going to be? Well, that's going to be d squared u dx squared times the derivative of x with respect to theta. Now, this term right here was already the derivative of x with respect to theta, so that's why we just end up squaring it. And the same is true for this one right here. You're just going to end up with another r cosine theta squared. So that's what this one right here, you're just going to end up with another one of those terms. So that's why there's a square. Now these derivatives, of course, are just the derivative of sine and cosine. So the derivative of sine is cosine, derivative of cosine is minus sine, and that's why there's a minus sign there. Anyway, we now have the derivative of u, the second derivative of u with respect to theta, and we also have the second derivative of u with respect to r, which we've just reproduced here. That's this one. So what happens if we add these two together? Well, let me just scroll up so we can just focus on this. So our objective is to add these two things together. So we have the second derivative with respect to r, and then we have the second derivative with respect to theta. So I've just written them all out together. Notice that we have a cosine squared term here and a sine squared term here, both attached to a second derivative of u with respect to x. Now if we were to add those together, we might be able to use the Pythagorean theorem. Unfortunately, there's an r squared term here. That's why we're dividing by r squared. We've written a 1 over r squared here. That's because that gets rid of this r squared and it gets rid of this r squared. We have an r over r squared here and an r over r squared here, so we're going to still keep one of these r's in the denominator, but our main objective is to get rid of that r squared and that r squared, because now if we add these two terms together, we have cosine squared plus sine squared is 1, and they both have the same coefficient. So that's right there. That's the second derivative of u with respect to x. Now, the same thing happens here. We have a sine squared and a cosine squared, and they're both multiplied by the second derivative of u with respect to y. So if you add those two together, you get the second derivative of u with respect to y. Now those together give you the Laplacian in Cartesian coordinates. Now what's left over, so here you're going to have an r over r squared, which that of course is 1 over r. And here you're going to have 1 over r. So you factor that out, which is right there. So this 1 over r and that 1 over r, you factor it out to get that. And what's left behind is just, well, might as well factor out the minus sign as well. That's that one. So this minus sign is that minus sign, and that give you that. And the stuff that's left behind, what is it? You have du dx times cosine theta, du dx times cosine theta, and here's a du dy times sine theta, du dy times sine theta. But that itself is du dr. So, just using the chain rule, du dr is this thing. So what do we have? Well, let's put all of this stuff together. So here we have a Laplacian of u, and here this term right here, this is minus 1 over r times the partial of u with respect to r. This term is u sub rr, the second derivative of u with respect to r, and this one is the second derivative of u with respect to theta. So solve for the Laplacian, and you have urr plus, you have urr, which is right there, and then we have a 1 over r squared times u theta theta. It's a little hard to see. Let me just underline it. That's this term right here. And then we want to take this term right here, and you just add it to the other side, and you get that. So this gives us the Laplacian in polar coordinates. We still have our second partial derivatives for r and theta, but it's not quite as straightforward as in Cartesian coordinates. Just has this little extra factor of 1 over r squared, and also this extra term 1 over r u sub r. In cylindrical coordinates, you get the same thing. You just add a uzz term. These are supposed to be z's. Let me just put a little line through them. So you end up with the same, this is the same as before, and then you just add in the u sub zz. That gives you cylindrical coordinates. In spherical coordinates, it's quite a bit more tedious, but you can, if you do all of the computations, you can compute the Laplacian in spherical coordinates, and it looks something like this. I won't go through that derivation.